The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
All right. Today we're going to start on a topic that's one of the harder topics that we cover this semester. We're going to start talking about molecular orbital theory. So this is a quantum mechanical description of the wave functions in a molecule. And we're going to use molecular orbital theory to look at the bonding in diatomic molecules. That's what we'll do for the rest of today. We'll look solely at diatomic molecules. And we'll look mostly at homonuclear diatomic molecules. At the end, we'll look at one heteronuclear diatomic molecule. And then on Monday, we're actually going to use a different kind of approach to look at the chemical bonding in molecules that are larger than diatomic. All right? So we're going to use molecular orbital theory for these diatomic molecules. And then on Monday, we'll go a little bit further. We'll look at bigger molecules, and we're going to use something else. We're going to use valence bond theory and hybridization ideas. All right? But today, we're going to deal with these diatomic molecules, the molecular orbital approach. All right? So here goes. We're going to start talking about hydrogen, as we usually do when we start talking about chemical bonding. So I'm going to represent my hydrogen atom here by this nucleus here, A. This is going to be hydrogen atom A. And I'm going to represent the wave function of that hydrogen atom by a circle, right? Because after all, the 1s wave function in hydrogen is spherically symmetric. So I'm going to represent it by a circle around the nucleus. So this is going to be 1sa. And then I'm going to, of course, have a second hydrogen atom represented here by this nucleus B and a circle around it because that wave function is spherically symmetric. And what I'm going to do in this molecular orbital theory approach is that I'm going to take these two wave functions and I'm going to bring them a distance of the bond length apart. So in other words, I'm going to take those two hydrogen atoms and I'm going to put the two nuclei here, A and B, at a distance of a bond length apart. And I'm going to let these two wave functions overlap, right? And these are wave functions. And what we learned a few weeks ago is that waves constructively interfere or destructively interfere. What we're going to do first here is we're going to let these two waves constructively interfere where they overlap. All right? So when we do that, this part of the wave function here is going to constructively interfere with this part of this wave function. And then the sum of those two is going to look something like this, right? Where now there's this constructive interference between these two nuclei, right? There's a lot of wave function right here because we superimposed those two wave functions, each from one hydrogen atom. And so there's constructive interference here. There's a lot of wave function right there. And in so doing, what we're going to call this resultant wave function here, we're going to call that the molecular wave function, or the molecular orbital, right? And how we got it was simply a linear combination of atomic orbitals, right? This is a linear combination of atomic orbitals. We just brought those two atoms close enough so that their wave functions overlapped constructive interference, and the result is a molecular wave function. Now, we're going to give that molecular wave function a name. We're going to call it a sigma wave function. The sigma designates the symmetry of that wave function with respect to the bond axis. This is the bond axis right here. The sigma represents the fact that this is cylindrically symmetric about the molecular bond axis. That's what that sigma means. And we're going to call this a sigma 1s orbital. It's a sigma 1s orbital because this was a linear combination of two 1s atomic orbitals. Okay? All right, but now what I want to do is I want to remind you that the physically significant part of this wave function was actually the wave function squared. Remember that? We talked about taking the wave function, squaring it, and that interpretation is a probability density. That was what was critical to our understanding of where the electrons are in a molecule. So that's what we're going to do here. We're going to take this sigma 1s molecular wave function now, and we're going to square it. And that's then proportional to or interpreted as a probability density. I'll just abbreviate that by P, but this is a probability density, remember, not a probability. All right? Okay, well, if that's the case, then I can multiply this out, right? Because sigma 1s right here, that sigma 1s is really equal to this linear combination of 1sa, 1sb. That's sigma 1s. So let me take 1sa plus 1sb, multiply it by 1sa plus 1sb. All right, that's what sigma 1s is. I'm just going to multiply this out. And when I do that, I'm going to get 1sa squared plus 1sb squared plus 2 times 1sa 1sb. All right? That's my probability density. But now, to make this a little bit more real for you, let's plot it. So I'm going to plot the probability density as a function of the position along the bond axis. So in this case here, the nucleus A is here, and the nucleus B is there. All right, so we have a molecule now. I'm just going to plot the probability density as a function of the position along the internuclear axis. And what's it going to look like? Well, it's going to look like this. It's going to look something like that. All right, where the probability density is the highest right at nucleus A, and the probability density is the highest right at nucleus B, because, hey, after all, you know, the wave function, any wave function, a S wave function, the highest value of that wave function is right at r is equal to 0, or right at the nucleus. All right? So that's what that probability density looks like. And I've just been informed here that the Xeroxing on that particular figure didn't turn out so well. All right? But that's what it should read, if you can't read it very well. All right. But the reason I plot this here is to contrast it with the following. Suppose I take just one hydrogen atom and the other hydrogen atom, but I take those wave functions and I just square them, and then I add them up. All right? So suppose I take a hydrogen atom with its wave function 1sa, I square it. And then I take another wave function for another hydrogen atom, 1sb, I square it, and I add those two up. In this case, what that's doing is taking two hydrogen atoms and just taking their wave function and squaring them. In this particular case, what I haven't done is I haven't allowed any interference to happen. I haven't allowed the wave functions to constructively interfere, right? I didn't add up these wave functions first before I squared them. I squared them and then I added them up. That's different than taking those wave functions, letting them constructively interfere, and then squaring them. And you can see the difference is when I plot this sum and compare it to that sum, right? So I'm going to plot now this sum. When I do that, it's going to look, well, it's going to look pretty much like this. But then right at the center, right here, hey, the probability density, right, for this case, for two hydrogen atoms, which are now non-bonded. They're non-bonded because I didn't let those two wave functions constructively interfere. The result is that this probability density right in the center here, hey, that probability density is less than what it would be if I let those two hydrogen atom wave functions constructively interfere. And that's the key in this chemical bond, is this term right here. It's this term that makes all of the difference. This is our constructive interference. This is the extra density that we get because those two wave functions have constructively interfered. That's what gives me this pileup of electron density right in the center here. This is the glue in this chemical bond. Okay? Makes sense? Okay? All right? Okay. So, we have formed now a molecular wave function by this linear combination of atomic wave functions. Now, what happens to the energy when we do that? Well, you can imagine what happens to the energy. The energy goes down. We're going to form a new molecular state. So let's draw an energy level diagram. All right, so energy going up here. And let me represent here by these two lines the energy levels of the separated hydrogen atoms. So I'm going to call this the 1s state on atom A, the 1s state on atom B. Hey, they're at the same energy. They're two hydrogen atoms. You can't tell them apart. And each one of them has an electron. Once we allow those two wave functions to constructively interfere, we're going to produce a new state. We're going to call that state sigma 1s. And that state is going to be lower in energy here than the two states from the individual hydrogen atoms. And that's good, because if it's lower in energy, hey, we got these two hydrogen atoms stuck together, right? We formed a chemical bond. These two hydrogen atoms aren't going to fly apart. That's what we wanted to do. Okay? And therefore, those two electrons here, one from each hydrogen atom, are sitting now in this new molecular state that we are calling sigma 1s. And the wave function then that describes the electrons in that state is the sigma 1s molecular wave function. Okay, that's great. Everything looks cool. Except now that, these are waves. So not only can waves constructively interfere, but hey, they can destructively interfere too. All right, so we got to take care of that case now, the case of destructive interference. So let's do that. All right, in this case, what's going to happen? Well, again, we have our 1sa wave function and our 1sb wave function. And now, when I'm going to bring these two together to the equilibrium bond length, AB here, what's going to happen is in destructive interference, this wave function is going to cancel this part of the wave function, right? When these overlap, and I take this minus sign here, or I'm superimposing two wave functions with different sign, we're going to have destructive interference, and the result is that the molecular wave function is going to kind of look like this. Okay, right in the center here, hey, there's going to be a node. There's a node because this part of the wave function exactly canceled this part of the wave function. Hey, there's no wave function right there. All right, because we have destructive interference. How are we going to label this wave function? Well, we're also going to call it a sigma wave function. It's sigma, that's the symmetry because it's cylindrically symmetric around the bond axis, right? But because it is a linear combination here that is a consequence of destructive interference, I'm going to call this sigma star. Sigma star 1s. And I'm going to call that sigma star 1s. That's an anti-bonding orbital, or an anti-bonding wave function. Okay? Now, how do I know that? Well, let's also calculate the probability density here for sigma 1s star. Hey, that's going to be interesting. So we got P, probability density, sigma 1s star, square it, right? So I have now a 1sa minus 1sb times 1sa minus 1sb. Multiply that out. So I get 1sa quantity squared plus 1sb quantity squared minus 2 times 1sa times 1sb. Hey, I'm now going to plot this on my graph here. All right? So this is what I'm plotting, right, on my graph of the probability density. When I do that, well, okay, way out here, right, on one end of the molecule, probability density is pretty low. Probability density goes to a maximum right at the nucleus, and then shoom, it plummets, right? And right at the center here, the probability density is 0 because the wave function is 0 because we had destructive interference. Okay? Hey, I want you to notice something. Probability density here is 0. It is even lower than this case. This case, which is just the sum of two hydrogen atoms, their wave function squared. In the case when the two hydrogen atoms aren't interacting, the probability density is some finite value. But in the case of this antibonding state, right, the probability density is 0. Goose egg, zip, nada. All of the other things, right? There's nothing there. This state here that we're forming, it's antibonding. It's not even non-bonding. Non-bonding, right, it's got more electron density. Fix the microphone here. All right. Non-bonding has more electron density than anti-bonding. Hey, this is anti-bonding, against bonding. Okay, that's the kind of state we just formed by destructive interference. So, where do you think in an energy diagram, where do you think the sigma 1s star level is? Well, you can imagine where it is. It's increased in energy. It's up here, sigma 1s star. And it turns out that the amount of energy above the energy for the two separated hydrogen atoms at this state lies is about equal to the amount of energy below the separated atoms that this state lies. These two energies are about equivalent. All right? So we now have a bonding state or a bonding orbital. We now have an antibonding state or an antibonding orbital. Okay? Now, when do we use that antibonding orbital? Well, we're going to see in a moment, but one case would be if we had an excited state of a hydrogen molecule. Hey, in an excited state, what we could do is we could take one of these electrons. My eraser is kind of wet here, so it's not erasing. Let me try this. I could take one of these electrons here, right, and populate it and put it in this state. That's the first excited state of H2, not H, H2. A second excited state would be take, hey, this is permanent chalk once it gets wet. All right. The second excited state will be taking that second electron and promoting it to this antibonding state. That would be the second excited state of molecular hydrogen. Now, I got to tell you, if you have these kinds of excited states of molecular hydrogen doesn't stick around, right? It's going to fall apart. Okay, but the ground state configuration of H2 has these two electrons here in the sigma 1s state. I also just want to point out here what the significance physically is of the separation in energy between the hydrogen atom states and the molecular hydrogen state. All right? Here's the significance. Remember, we drew an energy of interaction for molecular hydrogen. We talked about the general principles in the general attractions and repulsions that take place in every chemical bond. And the result was a curve that kind of looked like this, where this is hydrogen, two separated hydrogen atoms. This is, of course, the equilibrium bond length of H2. The molecules bonded here everywhere where this energy is lower than the separated hydrogen atom limit. Okay? Well, the physical significance here of this energy lowering of this state is, well, you know, this is essentially delta E sub D, right? This is essentially the bond strength of molecular hydrogen. That's what that is physically. Okay? Right? This energy from here to here, that's what it's going to take to pull the hydrogen atoms apart, the bond energy. Okay, so we took care of hydrogen. We have two molecular states, bonding, antibonding. For the ground state hydrogen, both electrons are in that bonding state. So now let's walk across the periodic table. Let's, okay, one other thing. If you were asked to write the electron configuration of molecular hydrogen in the ground state, what would you do? Well, the electron configuration of molecular hydrogen then, the way we would write it, is sigma 1s2, meaning two electrons in the sigma 1s state. And just to be complete here, you could write this antibonding state as sigma 1s star with 0 electrons in it. All right, that would be the electron configuration. Okay. Well, now, what we're going to want to do is to write the electron configuration for the next molecule as we walk across the periodic table. The next diatomic molecule. Hey, the next diatomic molecule is going to be helium 2, right? Okay. So, where are the electrons in the case of helium 2? Well, in the case of helium, each helium atom brings in 2 electrons. Each helium atom has an electron, has 2 electrons here in the 1s state. So I'm now drawing this for helium. All right? And the way we draw this correlation diagram, as it's called, is following the Southbow principle that we had for filling atomic states. Right? That is, we take the states, we order them in terms of their energy, lowest energy at the bottom, next highest energy, and then we start to put electrons in those states one at a time until we, starting at the bottom, starting at the lowest energy, until we run out of electrons. So that's what we're going to do for helium. All right, so what's going to happen? 2 of these electrons are going to be in the bonding state, and then 2 of these electrons are going to be in the antibonding state. And so the electron configuration here for helium is 1s2 sigma 1s star 2. That's the electron configuration for helium dimer. All right, but hey, this is interesting, because look, we have now in this molecular state 2 electrons that are at an energy that is lower than the 2 separated helium atom limit, and 2 electrons that are higher. Hey, it seems like there wasn't an overall stabilization of this molecule, right? Because we have one state that is lower in energy and another state that is higher in energy by the same amount, so the overall is, hey, zippo. Okay? And indeed, that is the case. So we've got a tool for counting or for telling how strong the bond is. And that tool is called the bond order. The bond order is defined as 1/2 the number of bonding electrons minus the number of anti-bonding electrons. All right, so in the case of helium-2, we've got 2 bonding electrons and 2 anti-bonding electrons. Hey, in the case of helium-2, the bond order here is equal to 0. When you have a bond order equal to 0, what that means is that you have no bond. All right? And indeed, that is the case. Helium-2 has no bond between them. Okay? Now, accurately speaking, helium-2 does have a bond between them, right? Helium-2 was discovered, so to speak, in 1993, and it was made under really very special conditions. And the bond strength here of helium-2 is a whopping 0.01 kilojoules per mole. That's for helium-2, right? Whereas, for example, the bond strength in hydrogen is 432 kilojoules per mole. So you can see how weak a bond that is. Effectively, this is no bond at all, right, practically speaking. And so molecular orbital theory really gets it right in the sense that it tells you, hey, there's no bond here. Okay? Okay. Great. All right, so now what we're going to do is we're going to keep marching across the periodic table. Actually, we've got to go down 1 row now. And let's look at the electron configuration for lithium dimer. All right. Now, if we're going to bring together 2 lithium atoms, lithium has 2 electrons that are in the 1s state and 1 electron each in a 2s state. And let me put them in. All right, so those are the electron configurations for the 2 separated lithium atoms. So how do we write this electron configuration? Well, again, we follow the Aufbau principle. We put 2 electrons here, 2 electrons here. But now, since we've got these 2s electrons, what we're going to have to do is to form molecular states, molecular orbitals, between these 2s atomic orbitals. And the 2s atomic orbitals form these molecular states in the same way that the 1s atomic orbitals do. Hey, they're all spherically symmetric, all right? So they form these orbitals in absolutely the same way. And so you get a sigma 2s bonding state and a sigma 2s star anti-bonding state. So if you want to write the correlation diagram, as it's called, for lithium-2, you take all of lithium's electrons and you now put it in the lowest energy state, put it in the next highest energy state, and put it in the next highest energy state. That's the correlation diagram. We ran out of electrons. We had six electrons total. So the electron configuration written here is this: sigma 1s2, sigma 1s star 2, sigma 2s2. All right, what's the bond order here? Hey, let's calculate it. We have 2 4 bonding electrons. We got 2 anti-bonding electrons. 4 minus 2 divided by 2 is 1. All right, we got bond order of 1. That means we got a single bond. That bond strength is 105 kilojoules per mole. That's a single bond. It's a weak single bond, but that's a single bond. Okay? Okay, what about beryllium? Let's make beryllium 2. Yes?
How did those electrons go off there? Just do that once over really quick.
I'm sorry?
The shifting of the 2s, the sigma 2s, how did those 2 get up there?
How did these 2 get up here?
Yeah.
Okay, these electrons, right, are the electrons on the atom. So the lithium atom has 2 1s electrons and 1 2s electron, okay? And this is the energy ordering for the atomic states in lithium, okay? The molecular state for lithium here, or the sigma 2s state, it is higher in energy than the sigma 1s star. This is the correct level ordering of the energies of these states. Okay? I didn't clearly explain that to you. All right? Does that make sense? Yeah. Okay. All right. Okay, so now we'll go to beryllium dimer. And now we got 2 2s electrons. So again, what do? We put 2 of the electrons in the lowest energy state, 2 in the next highest energy state, 2 in the next highest energy state, and another 2 in the next highest energy state. The electron configuration here of beryllium dimer, sigma 1s2, sigma 1s star 2, sigma 2s2, sigma 2s star 2. Oh, the 2's cut off here, but there's a 2. Okay. All right, what's the bond order? 0. There's no bond here in beryllium 2. Now again, there is a very weak bond. It's 9 kilojoules per mole. But for all practical purposes, there is no bond between beryllium 2, and this molecular orbital approach gets that right. Okay? Okay, well, now boron. Hey, boron has got a p electron in the atomic configuration. So now what we've got to do is we've got to look at the constructive and destructive interference between these p wave functions. All right? So we've got to do that. We've got to make molecular states. We've got to let the p wave functions, the p atomic wave functions, constructively and destructively interfere to make a new molecular wave function. All right, you ready? Here's how we do it. Here's the 2px wave function, or the 2py wave function. They look the same, right? One is just the x dimension, one is in the y dimension. They got a nodal plane right here. All right? What we're going to do is we're going to take that wave function, overlap it with the same wave function, 2px or 2py, from another atom. We're going to bring these two within the equilibrium bond length. We're going to let this part of the wave function overlap with this part of the wave function, and this part of the wave function overlap with this. And we're going to treat constructive interference first, and the result is a wave function that kind of looks like this. Okay? In the center right here, we got a lot of wave function, because right here we have constructive interference. In the center here, we got a lot of wave function. However, right along the internuclear axis, we got a nodal plane. Well, we got a nodal plane there because, hey, we had a nodal plane in the atomic wave functions to begin with. So that nodal plane is maintained here. We'll try this again. Okay. Now, this molecular wave function here, it's going to have a different name because it has a different symmetry, right? This wave function is not cylindrically symmetric around the bond axis. There's wave function above the bond axis and wave function below the bond axis, right? But not on the sides here. It's not cylindrically symmetric, so we got a new name for it. It's a pi wave function, and we're going to call it pi 2px or pi 2py. All right? Okay, it's going to be a bonding wave function. And of course, since it's a bonding wave function, if we look at an energy level diagram, right, the pi 2px and pi 2py are going to be lower in energy than the atomic wave functions, just like this. And since the 2px and the 2py in the atomic states are at the same energy, right, the pi 2px and pi 2py, hey, they're going to be at the same energy in the molecule. Okay? Make sense? Okay, let's do boron. Boron 2. Boron has got 1 p electron. It also has some s electrons, right? The s states are down here. I didn't draw them in on this diagram. I'm just treating right here the 2px electron. So what happens? Well, what happens is we're going to fill each one of these states with these p electrons. Now we're going to use Hund's rule again. Remember Hund's rule? It says that when you have states that are degenerate, that have the same energy, the electrons fill such that 1 electron goes in each state before you can put a second electron in either one of those states. Right? So that's what we did. 1 electron has to go here, 1 electron has to go here. You can't put 2 electrons in one of these states and leave the other one empty. That's not the lowest energy configuration, and you got to put those electrons in with parallel spins, not opposite spins. That's not the lowest energy configuration. All right, so that's the electron configuration here for boron 2. Sigma 1s2, sigma 1s star 2, sigma 2s2, sigma 2s star 2, and now pi 2px1, pi 2px1. Hey, let's calculate the bond order here. The bond order is 2, 4, 5, 6 bonding electrons, 2, 4, hey, 4 antibonding electrons, 6 minus 4 over 2 is 1. We got a single bond, 289 kilojoules per mole. Hey, that's a pretty good single bond, pretty strong single bond. Okay? That's boron 2. Let's do carbon. Well, carbon has got 2p electrons. So we follow the Aufbau principle. Hey, carbon 2, All 4 of those electrons then are going to go into these pi 2px and pi 2py states. And here's our electron configuration. We keep going. Here's the pi 2px2, pi 2py2. Okay, let's calculate the bond order. Bond order, number of bonding electrons, 2, 4, 6, 8 bonding electrons. Number of antibonding electrons, 2, 4. 8 minus 4 is 4 divided by 2. Bond order is 2, and we have a double bond, right? Hey, let's look and see how strong that double bond is. 599 kilojoules per mole. Hey, that's a pretty good double bond. Remember, the double bond is shorter, the double bond is stronger. All right, our single bonds were at 300, 400 kilojoules. This is almost 600 kilojoules. That's a strong bond. All right? And this molecular orbital picture tells you that you've got this double bond here. All right? By virtue of this bond order. Yes?
How do you know that the original electrons are in the 2p, x, and y as opposed to the z?
You don't. Okay? But I'm just about to treat the 2pz. All right? I'll tell you what our convention is. Good question. Okay? Okay. Here comes the 2pz. The 2pz atomic orbitals, by convention, the 2pz atomic orbitals we're going to put along the internuclear bond axis. So in the case of the constructive interference of the 2pz electrons, all right, in that case, these 2p wave functions look like this. They were no longer coming in, parallel to each other. Now they're coming in head on. All right? So that's our convention. The 2pz is going to be along the bond axis. 3pz is going to be along the bond axis. All right? So we're going to bring these two atomic wave functions in. We're going to let this part overlap with that part. And the result is a wave function that looks like this. Lots of electron density or wave function right in between the two nuclei. Here's a node, right? Here's a node. Well, these are nodes because there were nodes in the atomic wave functions to begin with. We're going to call this wave function the sigma 2pz. It's sigma because it's symmetric around the internuclear bond axis. Right? So that's the symmetry. We call that sigma. Okay. Now, what happens here? It turns out that this sigma state is a little higher in energy than the pi states in the next molecule. There's going to be some exceptions here in a moment. All right? So, nitrogen. Nitrogen has 1 electron in each one of the p states. Let's use the Aufbau principle to fill them up. Well, there it is. 2 here, 2 here, 2 there. All right? The electron configuration is the 1s's and the pi 2px2, pi 2py2, and now sigma 2pz2. Let's calculate the bond order in molecular nitrogen. Well, it's the number of bonding electrons. 2, 4, 6, 8, 10, minus the number of antibonding electrons. 2, 4, 10 minus 4 is 6 divided by 2, bond order 3. And hey, this means we got a triple bond. And boy, this better be a whole lot stronger. And it is. If you look at the bond energy in molecular nitrogen, it's a whopping 941 kilojoules per mole. We got a triple bond. This is a strong bond. This is a short bond. Okay? Okay. Now, next one's going to be molecular oxygen. And so now we've taken care of all of the wave functions, the molecular wave functions that we can form from the 2p atomic wave functions using constructive interference, it's now time to form some molecular wave functions using destructive interference. Let's do that. Let's go back to 2px and 2py. Okay? They're the ones that come in parallel to each other. All right, so as we bring them in, and we're going to go destructively, we're going to do it destructive interference. This part of the wave function is going to destructively interfere with this part. This part destructively interferes with that part. Hey, the result is something that looks like this. We got another node right along here, the center. That's a node because of this destructive interference. We got another node here where the plane of the molecular axis is. That's because these 2p wave functions had nodes in them to begin with, right? So that's what our wave function looks like. It's got some wave function in this quadrant, and this quadrant, and this quadrant, and this quadrant. This is another pi wave function because it's not symmetric around this bond axis. It is an antibonding orbital. It's pi star because this was formed as a result of destructive interference. So we have a pi star 2px and a pi star 2py. Let's put those on an energy level diagram. If they're antibonding, the energies are above those of the atomic states. All right? Now, let's write the electron configuration for O2. Here it comes. There's the 4 2p electrons for each oxygen atom. We're going to put 2 of them in the sigma 2pz, 2 in the pi 2px, 2 in the pi 2py, and then we're going to follow Hund's rule, and we're going to put 1 electron in the pi star 2px and 1 in the pi star 2py. We didn't put them both in the pi star 2px or both in the pi star 2py. And we put them in with parallel spins, not opposite spins. Thank you. You're going to ask me a question.
Sigma get to be lower energy.
Good question. I wanted you to notice that. Hey, here's a change. When we get to z equal 8, what happens? What happens is that they want to make this tough for you. And what's happened is that the sigma 2pz has dropped in energy compared to the pi 2px and pi 2py. At z equal 8, the energy ordering flips. At z equals 7 for nitrogen, pi 2px, pi 2py is lower in energy than sigma 2pz. But for z equal 8, oxygen and above, the energy ordering flips, right? Sigma is lower in energy than the pi. That is something you have to know. It has to do with the fact that the sigma 2ps has much more electron density in between the 2 nuclei. That electron density is so high that when the nuclear charge is that of nitrogen plus 7e, the nuclear charge actually isn't large enough to support all that electron density, right? But when you get to z equal 8, it is, and those energy levels flip. It's an exception, right? I mean, it's a change right there. It is one that you have to know, okay? Okay, here's the electron configuration for molecular nitrogen. If we go and we calculate here the bond order, what we find is the bond order is 2. That means we got a double bond, and that bond strength is 494 kilojoules per mole. Okay, so now we've got to make one more molecular orbital. And that other molecular orbital is between the 2pz states, and it's going to be destructive interference. So when this part of the wave function overlaps with this part of the wave function, we're going to cancel some wave function, right? And the result is that we're going to have a node right here in the center. These are the two nuclei. Here's our nodal plane. Hey, we've got a nodal plane right here anyway, and one here from the atomic wave functions. This wave function is a antibonding wave function. It's sigma star 2pz. And if you look at the energy level diagram, its energy, that antibonding state, is higher in energy than sigma pi 2px and sigma pi 2py. And so if we go to write the electron configuration for neon 2, well, all of the bonding and antibonding states are filled. The bond order in neon 2 is 0, right? There is no bond for all practical purposes in neon 2.